As we saw last hour, maybe our discussion was mainly about system design, how to use different amplifiers with different kinds of distortion in transmitters and receivers. While this hour we intend to look more into detail how to design suitable amplifiers for communications. And one thing that we didn't investigate into detail yet was the bias point of the active device we have in the amplifier. Most devices, say vacuum tubes, bipolar transistors, field effect transistors, allow the adjusting of the bias point. There are also some active devices that do not allow any adjustment of the almost any adjustment of the bias point, like traveling wave tubes, klystrons, or lasers in optics. There is no bias point with these devices. But with simple devices used in electronics, like vacuum tubes or transistors, we can adjust the bias point, and we can influence the efficiency of the output stage, though at a cost of a higher distortion probably. Class A, usually used for low signal operation, has the best possible linearity. It can work with also with small signals, but at the cost of a poor efficiency. Class B operation is better, much better than efficiency, but it has some moderate distortion. It's not too large, this distortion. Actually, we do not need push-pull operation like in audio amplifiers. In narrowband systems like radio frequency system, Class B, the distortion introduced by Class B amplifiers can be tolerated up to a certain level. And for the best efficiency, we could even go to Class C operation, so we don't care about bias at all here. And we don't care about bias at all. We get large distortion, but this distortion is not harmful for certain kinds of communication, like signals that have a constant envelope, like frequency modulated signal, analog signals, and even phase modulated digital signals. So there we could use Class C amplifiers directly. A subvariant here from Class B is Class AB, just because of this knee in the transfer curve. We want to avoid this knee and any kind of inaccuracy that can happen in this knee, and that was Class AB is a compromise between Class A and Class B. Class AB, actually, since the knee is not accurate, most amplifiers that we call Class B are really Class AB. So last hour we looked at Class A operation. Class A operation, we know many things about this Class A operation, even from last week, from the lecture from last week. We always dealt just with Class A operation. Also, amplifiers that do not allow any adjustment of the class of operation also behave similarly to Class A, except for the efficiency. But this hour we start our discussion with more efficient amplifiers, like a Class B amplifier. This theoretical improvement of efficiency is not that large. Other improvements in Class B are more important. We are going to see that later on. So now let's see why is the Class B amplifier so interesting for us in communication, even though it has quite a moderate distortion. It's causing quite a moderate distortion. Let's now draw the ideal Class B response, the simple Class B, not the dual Class B here. And this response is flat for one polarity of the signal, and it is linear for the other polarity. So we have no gain here. All this part of the signal, the negative part of the driving signal is lost, while the positive part, we have some useful transfer curve. So the Class B amplifier could also be considered as a rectifier. We still do not understand where is here the important point. The important point is that we can write this curve here with a knee as a sum of two curves. One is a linear response, and the other is such a triangular response, the other curve. So we have these two curves summed together. So this curve plus this curve summed together, they give a flat response, so no gain here below the bias point, and above the bias point the slopes of both curves actually add up together, so we get twice the slope, we get considerable gain here. We still do not understand what is that important for the usefulness of such an amplifier. So for both functions that sum up into the response of an ideal class B amplifier, the first function is a linear function. So this linear function has a bias term and a linear term, and this does not cause any distortion at all. It only provides useful signal amplification. While the second component of this function is a triangular function. This function around the bias point U0 is actually an even function. Even function around the bias point actually generates a polynomial response that only has even terms. It has the bias point, has the square term, the fourth power term, the sixth power term, and so on. There are only even terms present. So summing both outputs together, this is the output of the real amplifier. This was just our assumption that this function here is represented as a sum of a linear function and of an even function. Summing both together, we get a polynomial response that has the constant term, the linear term, and after the linear term there are only even powers of the input signal. So even terms, square term, fourth harmonic term, sixth power term, and so on. An ideal class B amplifier does not have any odd terms like third order, fifth order, seventh order, ninth order. Therefore, in theory, an ideal class B amplifier, yes, it does generate quite a substantial distortion with these even terms. But all these terms are even, so they do not contain any of the intermodulation distortion products, and that is the trick. We do have distortion in a class B amplifier, but this distortion in a narrowband system can be easily filtered out. In contrast with this is in contrast with other amplifiers that have odd terms, and if odd terms are present, then we are generating IMD. The class B amplifier does not generate any intermodulation distortion in theory. In practice, there is some intermodulation distortion because the real function, the real response of a class B amplifier is not ideal as depicted here. The real response function, maybe we could get a linear term, but it's very difficult to get a real triangular function with the vertex of this triangle right in the bias point. And the adjustment of the bias point may be quite critical to obtain the ideal, something comparable to the ideal class B response of the amplifier. But a class B amplifier, in theory, it does not generate intermodulation distortion, and that's the point. It generates distortion, but this distortion is not intermodulation related. Let's now see the other important point for class B operation, and that's its efficiency. So the real class B, if we decrease the amplitude of the sine of a periodic driving signal, also the power requested from the supply decreases. Say an ideal class B amplifier with no drive, it has no power supply consumption. And this is the important point because we want to amplify here small signals. While we are amplifying small signals, the output power decreases, the average output power decreases, but also the supplied power decreases. Therefore, the efficiency is much better. So it's not important actually what we told here, this difference between class A and B, the available 1 dB compression efficiency. This is not that large. This does not justify class B amplifiers because they are more difficult to use. But a much more important difference is the constant power supply consumption of the class A amplifier versus the variable power supply consumption for the class B amplifier. And this is actually decreasing with the power supplied. So the efficiency will be much better because of this power drain decrease here. This power drain decrease, unfortunately, is not curve parallel to the linear power, because the linear power increases with the square of the amplitude, while the supplied power, the requested from the supply, only increases linearly with the amplitude of the driving signal. So this increases linearly proportional. The current increases linearly proportional to the input power, while the power here, the output power, increases with the square of the power consumption. We do not have the power consumption anywhere here on this drawing. But still, the difference between the two, the difference in the interesting point region of operation at small signals, is stays much smaller than the difference in the class A amplifier. In the class A amplifier, the difference is here. This difference here is a ratio, because it is difference of logarithmic quantities, is much smaller, is much larger than the difference for the class B. So class B has a much better efficiency because of that. The power requested from the supply from class B is proportional to the square root of the actual output power divided by P1 dB, divided by the something close to saturation. And of course we have to multiply this by the power supply for the 1 dB point here, for the 1 dB compression point. This is almost our saturation point. So we do not have, no longer have a flat function like here, a constant supply, but we have something that is not proportional to the output power, but is proportional to the square root of the output power, at least over this region of small signals here. So the efficiency may be much better, the output power versus the supply power. Yes, it's at a 1 dB, and this is 50%, this is already better. But also this square root here helps a lot, because if I decrease the output power, also the efficiency here here it's the this term should be actually inverted here. This term here should be inverted, so this should be to the -1 here. This efficiency, because it takes its value in the denominator here, the supply power goes into the denominator, which I should invert actually this this ratio here. So it's P1 dB divided over square root of P output. So decreasing the let me see whether this is correct or not. So this is fixed. Sorry for this mistake. This actually the efficiency decreases, but that does not decrease that fast as in the class A. In class A, the decrease was proportional to the output power. In class B amplifier, the decrease is only proportional to the square root of the output power. So this decrease of the efficiency is much less than in the case of the class A. Class A has very poor efficiency for multi-tone signals like orthogonal and frequency division multiplexing. Class B is much better in that respect. And this is the important point. The important point is a much better efficiency for small signal operation, not really very small signals, but say some intermediate signals operation where we are still in the linear region, but we obtain, we need to amplify our signals linearly, like in orthogonal frequency division multiplexing. Yes, there is yet another thing we should consider about class B operation, about real class B operation, not theoretical. This was theoretical class B operation, a real class B operation. For real class B operation, this key here is not a real sharp key as we see it up here. The real sharp key here. This key is actually somewhat rounded. We use on many occasions we use class AB operation here. So an inaccurate key, or also this problem is worsened by an inaccurate setting of the operating point of class B. Actually, both the curves of the power supply and the linear power actually deviate from what we had before. And in fact, with most class B amplifiers are really class AB amplifiers. At very small signals, they turn into class A around this point here. And so these curves here actually rise up. Also, the power supply tends to become flat here, and also the linear power slightly increases because class A has more gain than class B. All this also has an effect of the intermodulation power generated by a class B amplifier. So in saturation, all amplifiers behave the same. Class A, class B, class C, they are all similar. In the linear region, the intermodulation power follows a straight line at an arctangent 3 angle here, because the intermodulation power increases with the cube of the input power, or with the cube with the output power. But after that, because of the inaccurate key, the intermodulation power turns back and may become even higher at lower signals. And this kink in the curve of the intermodulation power is a well-known feature of real class B amplifiers. So the inaccurate key actually makes things worse at very, very small signals. And when we are using class B amplifiers or class B AB amplifiers, we should consider this kink here. This kink is also known in audio amplifiers. It's called crossover distortion in push-pull amplifiers. In narrow band system, we do not need push-pull connection, though one can still use push-pull connection, but we don't need it. And this kink is always present at approximately the same output power, and this is actually a problem of class B amplifier. We have good linear to IMD ratio here with reasonable amplitude signals, but for very small signals things actually get worse, and this didn't happen in the class A amplifier. In the class A amplifier we went straight down along the arctangent 3 line. With class B amplifiers we have this kink here, and this is a problem. And this also influences our selection. If we are not using very small signals, then this is not a problem for us. If we are only limited with the maximum intermodulation distortion power, also we do not have a problem. If we need some linearity but not particularly high linearity, then this is okay. But if we go to choosing suitable modulations, we can do something with modulations. So QPSK modulation is a very efficient modulation for many communications, also satellite communications. But QPSK unfiltered QPSK requires a very broad spectrum. So we don't want that. We are going to filter the QPSK symbols. Filtering the QPSK symbols, the envelope of the output signal is no longer constant. The envelope changes, and any kind of amplifier can therefore generate intermodulation distortion with filtered QPSK. That make this intermodulation distortion is actually makes the sidebands regrow, the unwanted sidebands that are causing interference to other users. So the trick here is to filter QPSK in such a way that we are not going to use particularly low powers that can bring us into this region here, in the region of the kink in the intermodulation curve. We want to avoid this. We want to avoid these very low powers. And there's a trick how to do this. And the trick is to use two different sets of symbols for P quarter pi QPSK modulation. We use a set of even symbols that are depicted blue here, and a set of red symbols that are odd symbols in this diagram here. So symbols alternate: even, odd, even, odd, even, odd, and so on. From the theoretical point of view, there is no advantage of using quarter pi QPSK modulation. Both modulations have the same spectra, but there's a difference in the instantaneous output power. Conventional PSK may have direct transitions between these two opposite symbols, and this direct transition goes through the center of the complex diagram here, and going to the center, the power goes through 0, and this is actually a distortion. It generates high distortion here. We actually do not want to meet this region here, so offsetting the odd symbols by quarter pi, we do have transitions, direct transition, but only the transitions depicted here with these purple lines. And you see that all transitions between two neighboring signals, they never cross the center of the complex plane. So when you never cross the center of the complex plane, there is a minimum power, signal power, you can always avoid. So you with a quarter pi QPSK modulation, you can avoid this region here. This quarter pi QPSK modulation was invented on purpose to use the better efficiency, much better efficiency of Class B amplifiers, much better efficiency at lower than lower than saturation, lower than P1 dB compression point here. If you use some average signal power here, then this specially designed quarter pi QPSK modulation may be much more efficient because you avoid this region of distortion. This region of distortion is down here. This is one example. We also have other possibilities. We will see other possibilities later on with Class B operation, but this quarter pi QPSK was especially designed for Class B operation. There are other solutions that we can mitigate distortion in a Class B amplifier that we'll see later on. Finally, we have Class C operation. Class C operation does not have any bias. So for small signals do not get amplified at all in Class B operation. Class B operation operates stably only when fully driven to the full output power, when we have 13 dB of distance between linear power and distortion, intermodulation distortion. And Class C amplifiers are mostly used in this region here, so at full drive. The region in between, so 0 gain here for small signals and saturation, this region may be quite unstable because it depends on the supply voltage, on the temperature of the output stage, temperature of the device, temperature of the transistor, and so on. So this is quite difficult to use. But as we will see later on, this is today with OFDM. This region is also being used in Doherty amplifiers. So this is not to be forgotten. Only it's difficult to be used. So class C also provides the least amount of gain compared to all other stages. Class B provides more gain, and most gain is provided, the highest available gain is provided by Class A operation. Class C operation, also important for bipolar transistors, is less susceptible to secondary breakdown than Class A operation. So this is important to understand. If you have a transistor that is specified for Class C operation, this transistor may break down, may run into secondary breakdown when operated in Class A. So this is very dangerous for these devices, and also the high efficiency of the Class C amplifier also means that the dissipation of the transistor is smaller, so the secondary breakdown is much less a danger than Class A operation. Class A operation has a high power dissipation of the power device, especially without any driving signals. So it's important to know that a transistor designed for Class C amplification may actually break down in a Class A amplifier because of a different transistor design, different selection of the power equalizing ballast resistors, ballast emitter resistors in the bipolar transistors. MOSFETs do not have this problem. MOSFETs can easily work in Class A with any kind of modulation. So what about Class C? Now we are mostly using it here. What can we do with the Class C amplifier in practice? We may use Class C for modulations that use phase-only modulation of the radio frequency signal. So if I have here an FM modulator or a frequency shift keying modulator for digital transmission, like in a GSM phone, or an analog FM broadcast, all these transmitters, so analog FM broadcast, the GSM, and many other systems, may use the very efficient, very simple, very reliable Class C output amplifier. But this is not the only use of Class C amplifier. Another use is to actually operate the radio frequency output stage in Class C and apply envelope modulation to the power supply of this Class C. So we are actually changing here, sorry, the other way here. We are actually changing this power supply here by changing the supply voltage, by modulating the supply voltage. And in some occasions we can obtain very good quality modulation, quite linear, by modulating the power supply of the Class C amplifier. So the Class C amplifier here also works as a mixer to put our amplitude, low frequency amplitude modulation on top of the radio frequency carrier. This also works as a mixer. The output stage works as a mixer at the same time, and at very high powers this may be very efficient. So all the AM transmitters were all designed this way, that you had a modulator and a Class C amplifier. And this modulator was also a power amplifier because it had to modulate the power supplied, the voltage supplied to the output stage. So this is very simple design and was used with analog AM for broadcast and also for citizen band radio transceivers. This is quite uncommon today, so analog FM, AM broadcast stations are being turned down, and mobile phones probably replaced citizen band radio, so this is part of the past. But still, this technique has an advantage, and we see the advantage here. If we design these things in a particular way, we are using for RF amplification, we are using Class C amplifier. And this has good efficiency. But the modulator has to be linear, so it has to be Class A or Class AB, push-pull design, because we have a broadband low frequency signal here to modulate the whole chain. The trick here is at low frequencies we can afford switching amplifiers. So amplifiers that are actually designed as switching power supplies, operating at much higher frequencies that the signal to be amplified. So if this is audio frequency, so 10 kilohertz, we may operate the switching amplifier at 100 kilohertz or even 1 megahertz. And now, if we also require phase modulation, we could split, this is the input here, this is just, I forgot to translate this here, the input, this means input, hot. This is, we amplify separately the phase information. We pass the signal through a limiter, so we only get a phase modulated signal here without an envelope, and we amplify this with a Class C amplifier that also works as a mixer that adds the amplitude modulation in the final stage. Of course, we need an envelope detector here. And since this switching amplifier introduces delay, group delay, group delay is much larger for narrow band amplifiers, and switching amplifier is necessarily a narrow band amplifier, requires filters at the output, so it introduces group delay. And to have both the phase information and amplitude modulation, envelope information at the same time at the output stage, we have to delay here the phase modulation to get both signals in phase here on our antenna. We have to add a delay here, a delay line here, maybe also a narrow band delay line like a bandpass filter is also adds group delay. So for high efficiency, this is also an idea how to build amplifiers, though this is very difficult, especially it's very difficult to equalize the delay in the envelope section and in the phase section of such an amplifier. But this is an idea how to build high efficiency amplifiers. All with Class C that generates huge distortion, but this huge distortion is actually eliminated with the modulation in the same final output stage. The envelope modulation in the same final output stage, this is removed. We can continue then with Class B amplifiers. Class B amplifiers, we may have some modulations that are particularly designed for Class B operation. But in most cases, we amplify signals that we do not, that are not particularly designed, like analog television. Analog television had signals that were not designed according to the amplifier type of amplifier we are going to use. And very high power analog television transmitters required Class A, Class AB, or Class B output stages. So Class A already had some compression, a 1 dB compression. Class AB or Class B provided even more distortion. So just to avoid compression in these amplifiers, avoid signal compression, avoid saturation, the trick is to add predistortion. Predistortion that actually has the opposite transfer function of the power amplifier. If this is the power amplifier, predistortion should provide the opposite curve. So if the polynomial coefficients alpha 1 and alpha 3 of any semiconductor amplifiers have different signs, the predistortion circuit alpha 1 and alpha 3 should have the same signs to generate predistortion with the opposite sign. So we do not have phasor addition in phase, but we have phasors that are totally out of phase, so we have phasor subtraction. And we can subtract these two terms in the calculation of the PIP3 of the whole chain. Because this one has the opposite sign of the generated intermediate distortion, so we get the minus sign here. We see that with this arrangement of terms, we can get to very large PIP3, especially if the difference between these two terms is arbitrarily small. So with this simple, of course, the real equation is not as simple as this one here, but this equation tells us immediately that if IMD3 generated here and generated here actually do subtract one from another, they do subtract because the opposite sign of the alpha 3 here, then we can actually reduce our distortion or drive the amplifier to higher powers, improving the efficiency of the amplifier. Predistortion was typically used on analog television transmitters. It was something very difficult to adjust. It requires, with vacuum tubes in the output stage, it requires constant monitoring and constant adjustments. So it was really a little bit difficult to be used. Of course, we would not like that. It was also depended very much on the impedance of the antenna, because all distortions, all the IMD in the final stage, these curves here, depend very much on the actual impedance of the antenna. So this could not be used a fixed predistortion in a handheld radio, because in a handheld radio the impedance is changing, and of course also the requirements for predistortions are changing all of the time when the user is moving, holding this radio in his hands. So for handheld radio, a much better solution would be to design our modulation to avoid this dangerous region of high distortion of a Class B amplifier. This was actually used in mobile radios like the Digital Advanced mobile phone system in the United States, or the Tetra European system for mobile radios. So this was very, very complex. But what we are doing today is to have this predistortion done digital, in the still digital part of the signal, and it's an adaptive predistortion. So the transmitter actually measures its output and adjusts the predistortion to get the signal here, to get the signal to reduce the distortion of the output signal. And this is done today. The adaptive digital predistortion is done in OFDM transmitters. All OFDM transmitters have a digital predistortion, and not a fixed one, but an adaptive one, automatically adapted one. So manual intervention of the operator is not required. So these transmitters become simple. One solution that was also tried, but it was very inefficient, was the feed-forward amplifier. So the feed-forward amplifier actually included two high-power amplifiers. The first was the signal amplifier. The signal amplifier actually produced at the output some intermodulation distortion. So with careful design, we could, and using couplers, we could couple a sample of the input signal, a sample of the output signal of this amplifier, and subtract them. Simply connect them together with opposite phases to subtract the signals. What we are left with distortion, because this signal sample here has distortion, while this signal here does not have distortion. Since this signal amplifier has group delay, we should also compensate for the group delay with an additional delay line here to make this subtraction correct. What we get in the output, we get just the error, and the error is our intermodulation distortion. We now amplify this error with an error amplifier. This is also a Class A amplifier. Both amplifiers are Class A amplifiers. And this error is then subtracted through a coupler, through an output coupler. It is subtracted from the output signal. It is subtracted from the output signal, and since this error amplifier introduces some group delay, we have to compensate that group delay with an additional delay line here. So this thing actually does not have any feedback loops like in the adaptive predistortion. So from this point of view, this design is simpler. But it is very inefficient. I need two Class A amplifiers here. I need very accurate adjustments of the delays introduced by the amplifiers, of the group delays introduced by the amplifiers. It is very power inefficient. It was used, this amplifier design was used in UMTS base stations. So UMTS, when UMTS was invented, when it was designed, when it was put into service, UMTS was not really designed by engineers. Was more designed by businessmen that to make some business, and businessmen never care about the expenses. This was a very expensive way to build base stations of a mobile phone system, and that's the reason why UMTS is being phased out nowadays. They're turning down UMTS base stations and replace them with more efficient base stations. But part of the inefficiency of the UMTS base station was also given by this feed-forward design. This is all what people could do at that time. The real trick, the really efficient trick is different, a little bit different. The really efficient trick is not that young. It was already invented by an American engineer, Doherty, William Doherty, back in 1936. So what happened to this poor engineer? This engineer was asked to build a 50 kilowatt transmitters. And the businessman gave this engineer only 2 vacuum tubes for 5 kilowatts each. So he had 2 vacuum tubes for 5 kilowatts, and he was requested to build a 50 kilowatt transmitter out of it. Mission impossible? No, not mission impossible if you understand the operation of the amplifiers. He used the 2 tubes in parallel, but Doherty biased one of the tubes in class AB operation and the other tube in class C operation. They were operated in quadrature, so with 90-degree phase shift using 90-degree delay lines here. And for small signals, this carrier or main amplifier was only being used. Class C amplifiers did not react. Class C was still here in the small signal operation, so it did not react. Class C amplifier only became active at the peaks of modulation. So that's the reason why it's called the peaking amplifier. So now if I compare the efficiency curves of the efficiency versus the output power, class A amplifier, we have a rectilinear response here, if you remember. We had here it's linearly proportional, the efficiency is linear proportional to the average output power. For class B operation, we have a square root, and we have the square root function for class B, and class B, you see, at small signals is much better than class A. At large signals, the difference is not that large, but at small signals, the difference between class B and class A is much bigger here for small signals. And finally, we have Doherty, where we have this very good efficiency of the class AB amplifier for small signals, and then at large signals, the class C takes over, further improving our efficiency. So Doherty can achieve very good efficiency over a broad range of signals. But Doherty has a big problem. William Doherty could adjust his single transmitter build in 1936 for best performance, and this adjustment was quite critical. It required an operator, the transmitter, to have the correct adjustments. Therefore, William Doherty was forgotten for many years, up to the 21st century, when high efficiency became necessary for orthogonal frequency division multiplex for multi-tone modems. So, for OFDM, electronics made enough advancement that we could make all the adjustment of the bias points of these amplifiers and of the predistortion, of a digital predistortion, to have these things being done automatically. And then finally, the Doherty amplifiers could be used to reach high efficiency, extremely high efficiencies. And OFDM transmitters are now required also for broadcast, for digital video broadcast, terrestrial digital, or for LTE for mobile phones, all of them using OFDM. All of them are also using an adaptive digital predistortion, so the user does not know anything about these circuits here. He does not know anything about the Doherty. The digital part of the transmitter is actually adding already the required predistortion by the output stage to get best possible efficiency at low output distortion. So, Doherty, while it was unknown for many years in the 20th century, in the 21st century, Doherty is finally being used. It's finally being used because of this digital predistortion. It's finally being used even in small size transmitters like handheld phones, mobile phones. even these two amplifiers, on many occasions, these two amplifiers and some of the predistortion circuitry are integrated on a single chip. So this may be now in mobile phones, it may be integrated, these two amplifiers on a single chip, because adaptive digital predistortion takes care of the distortion caused by the output stage. Also, what is important, if we have digital predistortion, we can further drive this amplifier to achieve the highest output power, the highest efficiency in the output stage, so be up here. And frequently we specify not the P1 dB compression point, but the P3 dB compression point. If this power is significantly larger than the P1 dB, then this can be used, especially in multi-stage amplifiers, from the small signal part of the transmitter using digital circuitry, the D2A converter, and then many power amplifier stages to reach the output. Frequently P3 dB can be used. Why? It has some considerable distortion, but we can remove the distortion by adaptive digital predistortion. So this is the solution to go nowadays with transmitters. Though the transmitter becomes very complicated. It needs feedback from the output stage back to the digital circuitry to actually adjust the adaptive digital predistortion with suitable algorithms. Something that also happens, yet another effect that happens in amplifiers, most semiconductor amplifiers, most vacuum tube amplifiers, even vacuum tubes that do not have grids like traveling wave tubes, we have amplitude conversion, amplitude modulation to phase modulation conversion, AM to PM conversion, this is usually called. And this AM to PM conversion happens. Why? Happens because of the feedback capacitance we have in all active devices, in vacuum tubes, in transistors, and so on. So if we try to draw an equivalent circuit of this amplifier here, thinking only about RF, we have one signal path going through the amplifier, the other signal path going through the capacitor. With saturation, we model here the saturation. We actually, for modeling saturation, we insert a variable resistor here. As we overdrive the amplifier, this resistor increases in its value, so the output power is no longer increasing, the real output power available on its output. So, redrawing the phasor diagram for this circuit, we have the linearly amplified signal and the crosstalk signal going through the feedback capacitor, and the output signal is now the phasor sum of both these phasors. This voltage fall on here, this air saturation, and this feedback capacitor here. Now the phase angle of the output signal, also the amplitude is changing a little bit. Of course, saturation changes the amplitude of the output signal. But this phasor diagram is not drawn really to scale. This feedback is small, so most of the output signal is still provided by the amplifier. And it mainly generates a phase shift. This phase shift is always a delay. AM to PM conversion always generates delay. And this delay is a function of the input amplitude. We didn't expect that. If we had here a perfect limiting amplifier, we would obtain just the same output phasor just of changing amplitude. Now, besides the change of the amplitude, we also have change of the phase. Interestingly, in optical fibers, we have the same effect, the same AM to PM conversion, also in optical fibers. So we have if we have amplitude modulation on the optical signal, we get a change of the refractive index, and with the signal, the refractive index with the signal present, the refractive signal always increases. The N2 of optical fibers is a positive coefficient that has a positive sign, so the phase delay also increases. So even optical fibers behave exactly in the same way as bipolar transistors regarding intermodulation distortion. So this is yet another source of distortion, and we didn't discuss this source of distortion here with saturation. Talking about saturation here, we only consider the in-phase saturation, so just limiting the signal amplitude. Besides the amplitude, also the phase is a function of the driving signal power. So even here or here, we also have other sources of IMD, or even here we have other sources of IMD. Well, Class C amplifier is usually used at its maximum output power. This effect also should not be neglected in all amplifiers, though we usually just specify the PIP3. We just specify the power of this intercept point for the third order here or here. This PIP3 includes all effects, so a decrease of the amplitude and increase of the phase delay of the amplifier. But we didn't discuss this into detail. I just wanted to mention here that we do have this effect, AM to PM conversion, AM to amplitude modulation to phase modulation conversion is always present. We also discussed already the consequences of this effect, and we see the consequences, say, in QAM modulation. In the QAM modulation, the rotation of the constellation depends on the amplitude. So the 4 output signals are delayed more than the 8th central average, more middle power signals, and the innermost, the lowest power 4 symbols are even advanced in power because of the AM to PM conversion inside the QM modulation, and they actually make the error vector magnitude worse, increase, and they decrease the modulation error ratio. We also already discussed that 2 weeks ago talking about modulations, but this is just to show you where does this problem come from. This problem comes out of the Miller capacitance in an amplifier, or comes out of the AM to PM conversion in optical fibers due to the nonlinear refraction index of optical fibers. So with many different techniques we actually get back to the same problem with our modulation, because 16 QAM is also being used on high capacity transoceanic optical fibers. So we have exactly the same problem over there. Finally, we have the problem for today to finish this discussion of distortion mitigation. We should consider now multi-tone modems as used for orthogonal frequency division multiplexing. OFDM uses many carriers here, and with many carriers, if we require each signal to have an average power P0, each carrier, then the average power is simply the sum of all available carriers. So if we have n carriers, we have n times the average power of the output signal. This is not a problem in optical fibers, because with optical fibers we are using laser amplifiers that can handle the average power, can handle very high peak powers. This is the case for laser amplifiers. Unfortunately, there is no such thing as useful laser with electronics. With electronics, we are limited with the peak power, and the peak power grows with the square of the carriers, because at some particular point in time, the phasors of all carriers may sum up in phase, and if the amplitude sums is n times the amplitude of the single signal, then the power is n squared times the single signal, if we have in phase summation. This is just the maximum power. It is not present all of the time, but it is present at certain instance, and now the ratio between the peak to average power ratio is this ratio between the maximum power required just for the peaks divided by the average power supplied most of the time. If we have a large number of independent carriers, an OFDM may span from 48 to 27,000 carriers, 48 carriers in Wi-Fi, up to 27,000 carriers in digital video broadcast, terrestrial digital video broadcast, this large PAPR causes a very poor transmitter efficiency, since in theory we should design the transmitter for the maximum output power, and we are only operating at the average power. And if we have, say, 2000 or 8000 carriers, this drops the efficiency down to very, very, very low values. This is as long as we stay with theory. But in practice, if we have a large number of carriers, the power distribution of these carriers is a two-dimensional Gaussian function. That's a Rayleigh distribution of the power probability density. The Rayleigh distribution, we get it out of two Gaussian distributions in both real and imaginary axes of the signal. And the probability of having very high powers, so power much larger than the average power, is extremely small. So if this probability is extremely small, does it make sense to actually amplify signals out to the Pmax obtained here? Because if we clip the signal not reaching Pmax, we are going to add some distortion, but that distortion may be low enough for the required error vector magnitude or modulation error ratio. So we may tolerate actually some distortion caused by the output stage, by the transmitter output amplifier. We may tolerate some distortion because we are almost never going to reach that theoretical maximum power, especially with large numbers of carriers. And now we have to try to calculate what the distortion is if we limit the power of the transmitter to some value, some smaller value than this value given by the PAPR here, the power to peak to average power ratio. We can get along with much better efficiency from the transmitter with some distortion that's not going to corrupt that much our signal. What could also be done, we could also spare some carriers here to be adjusted by some mathematical algorithms to decrease this peak power. But these mathematical algorithms proved out to be way too complicated to obtain anything useful out of these transmitters, so we have to live with this peak to average power ratio. Now let's see what the calculation looks like. This circle here depicts the area of the signals that can be generated by our transmitter. Going outside the transmitter output stage is no longer to physically generate this power. We came up to here, so the border of this circle, this border represented by this circle, we cannot get outside of this circle. So we have small distortion inside the circle. This small distortion can be compensated by the digital predistortion. But there is nothing we can do outside this circle, because outside this circle, when the requested power is way too large, this power cannot be supplied by our amplifier. Even driving it into saturation, the amplifier is no longer able to supply this power, and well, we cannot do any digital predistortion just to make digital magic to supply analog power and the output. So this is a really analog limitation. So we can control the distortion inside the circle, and we can keep it arbitrarily small. But outside the circle, we also, the amplitude, the best we can do, we get to the dotted line here, to the perimeter of this circle with the generated output power. And we also have this phasor here, the red phasor, actually describes the error signal. The error signal magnitude, square root of the error signal power. And we are interested in how much error power do we get here, both due to saturation of the amplifier depicted by the circle and to AM to PM conversion. So this signal is also phase delayed. But we can handle the phase delay in digital predistortion. We can handle it. We could measure this error power as a function of the power requested by the transmitter, but this is measured but demanding. This is a very demanding measurement of the thing to be done, and we want to calculate this error power here, making the calculation on this triangle using the cosine law on this triangle, this with this green phasor here, blue phasor and red phasor. Green phasor is required power, blue phasor is actually supplied signal, and red phasor is the error. We want to know what the error power is. So to get the average, we can compute now the error vector magnitude, knowing the average error power, because the average error power will define the radius of this circle, this noise circles around here. Noise or error or distortion. Noise, here noise also includes distortion here, and distortion is the problem we faced here. So to calculate the average power, we should multiply the average power density here with the average power, the error power of P, we calculated here. We should multiply it with the power, with the probability density of having this peak power here, and we should integrate this over all possible powers here. So probability density that we require such power, and the actual power, the error power we obtain at this power here, and we calculate the actual power out of here. So this is very difficult to do. Because we don't know what the error power is going to be. But there is a very rough estimate we can make with our calculation. And the very rough estimate is that if we are inside the circle, so if our power is below, the requested power is below P1 dB, we can correct everything in digital predistortion. So the error power is now equal to 0. But if we are outside the circle, the error power, we can just say that this error power is equal to the whole power we are requested. This is actually an overestimate of the error power, but it's not that bad an estimate, as we shall see it later, because this error power due to AM to PM conversion is quite large. And if this peak power is very large, the difference is small here. So we actually, this is an overestimate, but an overestimate only here, if we overestimate the error power, we can hope that in the real world the error power will be smaller. What happens now? Now we should evaluate this integral here using this estimate for the power. So since this is 0 below P1 dB and is equal to P above 1 dB, we just add P here. We just add P here to the known Rayleigh distribution here. We just added the P, our estimate P, to the Rayleigh distribution here, and try to evaluate this integral. We can evaluate this integral, and we have to go per partes here to evaluate this integral, the actual value of this integral, and we can plug now in this value our actual powers. We can plug in P1 dB of our amplifier. P1 dB is the information we have our amplifier, and the required average power we request for this amplifier. And from this probability, from this average error power, we can calculate the error vector magnitude, which is the square root, because error vector magnitude is given with amplitudes, of the error power divided by the average power. Our average error power divided by the average power. This for OFDM is a very simple expression. If we plug this solution of this integral for our rough estimate here, we get down to this formula for the error vector magnitude. Now this formula will not tell you much, but if we have P1 dB much larger than average power, this thing goes to 0. And in fact, we try to now to plot this solution. So plot this ratio here in decibels of P1 dB over average requested power, and the error vector magnitude we obtain. So if the P1 dB, if the saturation of our amplifier is just equal to the average power, we obtain a useless error vector magnitude of 86% here. At 5 dB, still things look very bad. We get lots of distortion even at 5 dB. Back off of the OFDM transmission. This ratio is also called the back off the transmission. We roll down the average power for a given P1 dB. But at 10 dB, error vector magnitude becomes totally useful. So 2.2% error vector magnitude could even QAM 16 could work with 2.2% error vector magnitude. So this is already a useful value. And at 15 dB back off, the error vector magnitude practically goes down to 0. And it's really 0 for 20 dB. For 20 dB, it goes really to 0. So our interesting range of the transmitter back off is between 10 dB and 15 dB. 10 dB for single modulations like QPSK over OFDM, and QAM 64 or QAM 56 for 15 dB transmitter back off. What does that mean? 10 dB back off. 10 dB back off means for a class A amplifier 3% efficiency. 15 dB back off for 30% efficiency at the 1 dB compression point means 1% total efficiency of the amplifier. So a simple class A amplifier, let's go back now to the picture of the class A amplifier here. This ratio, this P out dB is really our average power. If we have 10 dB here, we get 3% efficiency. If we have 15 dB, we get 1% efficiency. So class A amplifier will go in with OFDM signals, we go between 1 dB and 3 dB efficiency. This is okay for low power systems like Wi-Fi. For higher power systems, we resort to Doherty amplifiers with digital predistortion, with digital adaptive digital bias adjustment of both stages to have better efficiency. And with OFDM, we may get even at 10 dB back off or 15 dB back off, we may get an efficiency, say, up to perhaps 10%. 10% total efficiency, while lower values are more typical for, say, broadcast transmitters is usually between 5-6% are digital television broadcast transmitters. So this is a rough estimate, a very rough estimate. It's a worst case estimate actually. It's for the error vector magnitude, but these figures actually hold very well in the practical world. In the practical world, the efficiency of these transmitters actually run at these values. So this is all about today topics about distortion mitigation. So next time we have to change topics. We could not, in this short course, we could not yet investigate all properties of amplifiers, but I hope we just talked about the most important properties of amplifiers in communications techniques. Next time we are going to talk about oscillators. Even oscillators play an important role in communications equipment, and we have to look at oscillators in detail. But for amplifiers, that's all for today.